So first of all, the bandwidth was adequate. It was more than required. So we can throw a lot away if you want, but we will, next week we'll discuss that and try to do it in the smart way. So the frequency compensation was required if we are looking for a maximally flat frequency characteristic, and we had a lot of overshoot. We had some like 4 dB peaking at 1.5 gigahertz. Phantom zero at the input is the most cost-effective solution for this amplifier. It is not a general conclusion. Definitely phantom zero will be always the most cost-effective if you can realize it, but not always at the input, of course. It can be in the feedback network, it can be at the load. In our case, it was at the input with the resistor. It is the lowest and negligible influence on other performance aspects, and that is what we call cost effective. It means that and sorry, there's an extra thing, and that is what we are going to stress next time. It acts as an input filter for out-of-band high frequency EMI. Because remember, it was a pole in the asymptotic gain, so high frequencies beyond the frequency of this phantom zero are attenuated before they enter the amplifier. And that's a nice thing, because at that point you probably don't have much loop gain left, and if you don't have much loop gain left, there's not much reduction of distortion left, so then it is nice to keep the amplitude of interference signals as small as possible. So that is what we are going to do next. We are going to use this technique to see if we can limit the bandwidth of our antenna, active antenna, in a smart way. Bandwidth limitation with phantom zeros, and it is, as we can conclude now already, a powerful method for reduction IMD caused, or intermodulation distortion, caused by out-of-band EMI. So that's what we're going to do next Tuesday. I see, I have a question. In which cases phantom zero compensation is not possible? Well, as I told you, phantom zero compensation, it's in the book, by the way, so if you go back to the homologation program, you will find answers to this, but the idea is this. A phantom zero uses an existing attenuation in the loop. Well, if there is no, then you cannot make a phantom zero. For example, consider that I am making an amplifier, a unity gain voltage amplifier, and my controller would be an op-amp with almost zero output impedance. Then any load impedance does not put an attenuation in the loop. And if my controller also has an infinite input impedance, the op-amp, then the feedback network and the source impedance also don't introduce attenuations in the loop. So a unity gain feedback voltage amplifier is very difficult to compensate with the phantom zero, with an op-amp, because there's no attenuation in the loop. We have seen, by the way, a few lectures back, that the unity gain voltage follower with a CS stage, and that we called a common drain stage or the source follower, there was attenuation in the loop. And there was a low loop gain. But there we have used phantom zero compensation. And maybe now you understand better if you go back to that lecture. I think the video is already uploaded. If you go back to that lecture, you will also appreciate more the effect of the phantom zero.